So, hello everyone, welcome to the IISc MSR Theory Seminar Series. This week we are delighted to again have Professor Karthekeyan Chandrasekaran as our guest speaker. Professor Karthik is an associate professor at the Department of Industrial and Enterprise System Engineering in UIUC. He completed his PhD in the Algorithms, Combinatorics and Optimization group at Georgia Institute of Technology. Before joining UIUC, he was a Simons postdoctoral research fellow at Harvard University. His research interests lie in the area of combinatorial optimization, integer programming, probabilistic methods, and randomization. He has regularly published in top-tier conferences like SODA, Fox, Scott, and so on. He has kindly agreed to give a two-part talk titled Partitioning over Submodular Structures, and the first talk happened last week, and today is the second part of this talk. So let's welcome Professor Karthik, and all yours.
Thank you, Ramesh. Thank you again for inviting me. Today's talk, we'll do a board talk. So it's going to be a bit more of combinatorial optimization. And once again, please feel free to interrupt and raise questions if there are any. Again, the goal is not to cover too much material, but to convey some important, some nice proof ideas. Okay, again, let's quickly recap submodular functions. Recall that a set function f defined over a ground set V is submodular if for every pair of subsets A and B, the sum of the function values on A and B is at least the sum of the function values on the intersection and the union. A well-known example of a submodular function is the hypergraph cut function. Given a hypergraph over a vertex set V, consider this function D, which is defined over subsets of vertices. The function value on a subset S of vertices is defined to be the number of hyperedges intersecting both S and the complement of S. This function is submodular. This can be shown by verifying this inequality by counting argument. And turns out this function is also symmetric. Recall that a function is symmetric if the function value on a subset A is equal to the function value on the complement of A. The number of hyperedges crossing S is equal to the number of hyperedges crossing the complement of S. So this function, the hypergraph cut function, is in fact symmetric and submodular. In this talk, we will be interested in submodular k-partition problems. In submodular k-partition problems, we are given a submodular function f via an evaluation oracle, along with a fixed constant k. Again, think of k as 2, 3, 4, 5, and so on. It is a fixed constant. We would like to find a k-partition of the ground set, that is a partition of the ground set into k non-empty parts, so as to minimize an objective of interest. If the objective of interest is the sum of the function values of the parts, the problem is known as min-sum submodular k-partition. If the objective of interest is the max of the function values of the parts, the problem is known as min-max submodular k-partition. And as special cases of min-sum submodular k-partition problem, we have the min-sum hypergraph k-partition problem. Here, this is in fact a special case of min-sum symmetric submodular k-partition. Min-max hypergraph k-partition is a special case of min-max symmetric submodular k-partition by simply taking the cut function of the hypergraph as the submodular function. And hypergraph k-cut is also a special case of min-sum submodular k-partition, where the submodular function is asymmetric. So all these three hypergraph k-partition objectives are special cases of submodular k-partition objectives. And ideally, we would like to know how to solve submodular k-partition. Recall that for k equals 2, both min-sum submodular 2 partition and min-max submodular 2 partition are equivalent, and they can be solved in polynomial time. and this, sorry, they're not equivalent, but for symmetric submodular functions, they're equivalent. Okay, quick background. For the case of k equals 2, min sum submodular 2 partition is polynomial time solvable. This is because you can, in order to solve this, it's sufficient to solve min st cut for submodular functions. What is min st cut for submodular functions? Given subsets S and T of the ground set, we would like to find a subset A that contains S and is disjoint from T, so as to minimize the sum of the function value on A and the complement of A. This is min st cut for submodular functions. Min st cut for submodular functions is essentially submodular minimization. This can be solved in polynomial time. And once you can solve min st cut, you can solve global min cut. So min sum submodular 2 partition is polynomial time. Do keep this in mind. Min st cut for submodular functions can be solved in polynomial time. In fact, it can be solved in deterministic polynomial time. We are going to rely on this result shortly. Right. So this is the case for min sum submodular 2 partition, but min max submodular 2 partition is NP hard. In fact, min max modular 2 partition is already NP hard. Integer 2 partition is NP hard. So there is no hope to do anything interesting for min max submodular k partition. As I said, the entire talk is about polynomial time algorithms, so we won't talk about approximability and such. Right. So given this status for 2, we immediately get the rest of these cells as well. Min sum symmetric submodular 2 partition, min max symmetric submodular 2 partition. Note that for min max symmetric submodular 2 partition, if the function is symmetric, then it reduces to min sum submodular 2 partition. It can be solved in polytime. And these other special cases for k equals 2 are also polytime. For the case of graphs, turns out min sum graph k partition is polynomial time for every fixed k. This was shown in the late 80s, early 90s by Goldschmidt and Hochbaum. And for min max graph k partition, this is also polynomial time for every fixed k. This follows via results by Karger and Stein. Right. So given this, there are two natural questions here. Firstly, can we solve min sum submodular k partition for larger constants k? K equals 3 or 4 or 5 and so on. And can we solve min max symmetric submodular k partition for larger constants k? Yeah, ideally we would like to know the answers to these two questions. And if not, then it's helpful to look at these special cases. Can we solve min sum symmetric submodular k partition for larger constants k? In fact, this was claimed to be solvable in '98 by Querant, but he subsequently retracted this, so we still don't know an answer to this. And so, yeah, then these are the natural questions. Can we solve these for larger constants k? And some of these were discussed by Lawler as early as '73. The results I mentioned in the previous talk, we now know how to solve hypergraph k cut. This is polynomial time for every fixed k. We first gave a randomized algorithm. We discussed this randomized algorithm in the previous talk. And then subsequently, we gave a deterministic algorithm in 2020. The deterministic algorithm for hypergraph k cut inspired us to look at min-max symmetric submodular k partition, and we were able to get a polynomial time algorithm for min-max symmetric submodular k partition for every fixed k, which in turn implies that min-max hypergraph k partition is polynomial time for every fixed k. And this answers the open question by Lawler. And in the previous talk, we saw the randomized algorithm for hypergraph k cut. In today's talk, I'll focus on min-max symmetric submodular k partition. I'll describe the algorithm and the correctness analysis. The goal of the talk will be to give you the full details of the correctness analysis. And all algorithms in this line of work that I've shown, all these results that I've shown, the algorithms are simple 4 or 5 line algorithms. The non-trivial aspect is the correctness analysis. Right, so that's going to be the plan. I'm going to jump into min-max symmetric submodular k-partition questions. Yeah.
Yeah. So this graph cut results, these are for weighted graph cuts or unweighted, like just edge counting.
Everything is for weighted case. I like to think about the unweighted case just for the sake of simplicity, but all results, even for hypergraphs that I've shown, are for the weighted case.
Excellent. And so, so what you have here are two ends of the spectrum, right? You're looking at in some sense, the L1 norm and the L infinity of these. Have the P norms been studied as well? So you find a partition such that then you look like V1 through Vk and the P norm of these.
Of the cut values of the parts should be.
Yeah.
So, well, we don't know the answer to L1 itself.
But L1 is this sum, right?
Yeah, so we don't know the answers to L1 itself.
Oh, okay. I was thinking of maybe for k equals to 2.
K equals 2, I think for k equals 2, symmetric submodular is not interesting. L1 solvability implies LP is also solvable, right?
Yeah.
And for submodular functions, I don't know. For k equals 2, LP norm, is it solvable? I don't know.
Yeah, but the NP hardness seems to suggest that, yeah, like after a while, like very quickly it should start.
Yeah, I would imagine, yeah, P greater than 1, it should become NP hard. I haven't thought about this.
Yeah. Okay, thanks.
Right. Okay, so the rest of the talk will be about min-max symmetric submodular k-partition. What is the problem again? We're given a symmetric submodular function via an evaluation oracle. Along with the fixed constant k, we would like to find a k-partition of the ground set so as to minimize the maximum function values of the parts. Now, the one way that so yeah, I'm going to go into sort of a lecture mode here. One approach that you would think of to solve this problem is, well, let's try to find one of the k parts of the optimum k partition, and then you will strip this out and try to solve a k-1 partition problem and recurse for that. Okay, this is one way to try this, but what is the issue with this? Does anybody see what is the problem with this approach? Suppose we find one of the k parts of the optimum k partition. Let's say we find V1, the one of the k parts. Then why don't we simply delete V1 and recurse on the remainder and solve the problem? What is the issue with this approach? One can always look at the function restricted to the remaining set of elements.
I guess you lose symmetry, like you lose.
Yeah, so that's the problem. The function restricted to a subset of the ground set is not symmetric anymore. So you lose the symmetric nature of the function if you do this approach, finding one of the parts and deleting it and looking at the restriction. You lose symmetry. The restricted function is not symmetric anymore. It will be submodular, but it will not be symmetric, and then you run into problems. So this is the issue. So in a sense, if you want to solve this problem, you should be finding all k parts simultaneously, all k parts of the optimum k partition simultaneously. Okay, so this is one of the bottlenecks when we are thinking about this. And somehow symmetry should be crucial, right? Because even for min-max submodular 2 partition is already NP hard, so symmetry should be crucial. So losing symmetry is not the right way to go. The main technique here that we use to solve this problem is to use min-ST cuts to recover the parts of an optimum k-partition. We do this in one shot. We are able to find all k parts of the optimum k-partition using these min-ST cuts. And to explain this technique, I'm going to work under the simplifying assumption that the function values are distinct. That is, the function value on a set B is not equal to the function value on the set A, provided B is not A or the complement of A. We know that f of A is equal to the f of complement of A, but for any other set B, the function value is not the same as the function value on A. I'm going to work under this simplifying assumption. In fact, when I was thinking about this problem initially, I was working under the simplifying assumption, and this assumption can be relaxed with a little bit more work, but turns out this was helpful while thinking about the problem. And one of the advantages of this assumption is that if you consider min-ST cut, it becomes unique. Min-ST cut for any fixed S and T is unique because of this assumption that function values are distinct. And yeah, there are two ways to relax it. Either in your algorithm, you have to break ties carefully, or you can enforce this assumption by fudging the function values by a small amount, by perturbing the function values by a small amount. So it's not a very restrictive assumption. Right. Under this assumption, we prove a clean structural theorem to identify the parts of the optimum k-partition. So let's say we look at the optimum k-partition, V1 through Vk. This is the optimum k-partition. Now, here is where we show. Let's look at one of the parts V1. Suppose I want to recover V1. Let's look at V1. We show that there is a subset S inside V1 and a subset T in the complement of V1, such that V1 bar is the unique min-ST cut. Recall that min-ST cut is unique for every fixed S and T. So we find some such sets S and T for which min-ST cut is exactly V1 bar. And so far, this is trivial, right? I could simply have taken S to be V1 and T to be V1 bar. So this is trivial. The non-trivial aspect of the result is that these subsets S and T are of small size. They're of size at most k minus 1. Now let's interpret this theorem. What does this say for k equals 2? What does it say for k equals 2? Well, it simply says that look at optimum 2 partition, V1, V2. There is an element S, so k is 2, so k minus 1 is 1. So it says that there is an element S in V1 and an element T in V2 such that min-ST cut is exactly V1, V2. Okay, this is obvious, right? The global min cut is the min-ST cut for some particular S and T. So this is for k equals 2, this is the obvious statement. And the main contribution here is a generalization of this obvious statement for larger constants k. Right. Now, why is this theorem useful? Any questions on interpreting this theorem? And we prove this theorem to not only for V1, but for every part, V1, V2 up to Vk. For every I, this theorem holds.
And you only need this as an existential guarantee. That is, since
right.
K
So
is a
we only
constant,
need
yeah, you can guess the parts and then run. Yeah, we'll probably do it some. Yeah, okay.
Yeah, so I'm going to describe the algorithm. Why is this theorem useful? It allows us to enumerate all parts of a collection of subsets containing all parts of the optimum k-partition. So here is how we would enumerate. So initialize this family F to be empty. Now for each subset S and T of the ground set of size at most k minus 1, you compute the minimum ST cut U bar and add U to the family F and look at this family at the end. The claim is that this family F contains V1. Let's first talk about V1. Why does it contain V1? Well, the structural theorem says that there is a subset SNT of size at most k minus 1 such that minimum ST cut is exactly V1, V1 bar, and V1 will be added to the family F. So this family F contains V1. And in fact, the structural theorem holds for V2 through Vk as well. So the family F contains V2 through Vk as well. Now, what is the size of this family? Well, the size of the family is n to the order k, because the size of subsets S and T are k minus 1, at most k minus 1. So the size of the family is n to the order k, and the time to compute this family is n to the order k min ST cut computations. And recall that min ST cut for some modular functions can be solved in polynomial time. So the runtime for this procedure is polynomial time because k is also a constant. K is 2, 3, 4, 5, and so on. So we have a polynomial sized family, n to the order k sized family of subsets containing all parts of the optimum k partition. So once you have this, the algorithm is immediate. You simply look at all possible k tuples of the family that form a k partition of the ground set and return the cheapest with respect to the max objective. Right. So that's the algorithm. The runtime is the time to compute the family, which is n to the order k min ST cut computations, plus the size of the family, choose k. The size of the family is n to the order k. So overall, the runtime is n to the order k squared. And the number of function evaluation queries is dominated by the runtime of the procedure. It's the n to the order k min ST cut computation. So the number of function evaluation queries is n to the order k. So that's the complete description of the algorithm. As I said, the algorithm is simple, 4-line algorithm. The non-trivial aspect is the structural theorem. Any questions on this?
So this does up to like quasi-poly, like if k is like it's, the k can be super constant, but you'd get a like a quasi-polynomial. So it's sort of smooth in that sense.
Right.
And do you have like a sense of whether this is tight? Like there are instances where S and T are indeed of size k minus 1, or those are easy to construct?
Yeah, the structural theorem is tight. Yeah. I think, yeah, it's tight. I don't recall the example now, but we check this. Yeah.
Okay.
Other questions?
So in the structure theorem, do we require this VI complement to be the unique min cut?
Right. So recall the assumption that I made. Function values are distinct. So min ST cut will automatically be unique.
Okay.
The rest of the talk, I want to tell you the proof of this structural theorem under the simplifying assumption. Yeah, I'm going to do a board talk for the rest of it, proving this structural theorem. And recall the definition of symmetric and submodularity for set functions. The crucial aspect should be symmetry, right? How are we going to exploit symmetry? Turns out symmetric submodular functions are also Poisson-modular. Poisson-modularity says that for every subsets A and B, the sum of the function values on A and B is at least the sum of the function values on A minus B and B minus A. Poisson-modularity is, you can prove that symmetric submodular function is Poisson-modular by simply applying the submodular inequality along with symmetry. So f of A plus f of B is equal to f of A plus f of B bar, and apply the submodularity inequality to A and B bar, you get the A minus B and B minus A on the right side. Okay? So Poisson-modularity is easy to show for symmetric submodular functions. And this is the crucial property of symmetric submodular functions that we will exploit. And I'm going to shift to the board now. But these are the assumptions that we're going to use. The given function is symmetric, submodular, which in turn implies that it is quasi-modular. And I'm also going to assume that the function values are distinct. And we're going to prove this structural theorem. Any questions before I shift to the board? Okay, let's shift to the board. I'm going to share the screen here, but you can also see the board. In case you want to scroll through the board, you can use the link. I've sent this in chat. You can use that to scroll through the board. Okay. Right. So can everybody see the board?
Yes.
Okay, so we have a function which is symmetric submodular. Note that I'm not going to assume anything about non-negativity here. The function can take negative values. I'm not going to assume anything about that. The assumption is that the function values are distinct. So f of b is not f of a whenever b is a subset of a and b is not a and the complement of a. And let's look at the optimum k partition. I'll denote this by v1 through vk. This is the argmin of the max of f of vi, I and k, where v1 through vk is a k partition of the ground set. And I'll denote this value as opt. The min-max value is opt. Now, I'll prove a slightly stronger version of the theorem. Instead of recovering just V1, let's look at an arbitrary two partition such that the function value of this two partition is at most opt. This is an arbitrary two partition. In particular, V1 bar also satisfies this. And we will show that an arbitrary such two partition can be recovered via min-st cuts. So we'll show that there exists st subset of V such that u bar is the min-st cut. Recall that min-st cuts are unique and the sizes of s and t are small. This is a slightly stronger version, but turns out that this is easier to prove. And recall what is argmin st cut. This is the argmin of f of a, where s is contained in a and a is disjoint from t. Okay, so this is the stronger theorem that I'm going to prove. And to prove this, we are going to prove a slightly simpler version of the theorem. Okay. So far, I'm always going to fix u bar. In the rest of the talk, we're going to fix u bar such that the function value is at most opt. First,
the stronger theorem. The stronger theorem, what is the value of k here?
The stronger theorem meaning?
No, the theorem one. So k isn't. What does k mean here?
Oh, k is the k partition, right?
Right, but in the statement of the theorem one, there is no k partition or anything. Right?
Oh, I've stated all the assumptions here.
It's the opt that dictates the thing.
Yeah, if I care about k partition, so okay. All the assumptions are I'm going to use that for all the theorems henceforth. So I stated all of them before.
Okay, so U is any partition which says that f of u is less than that k partition opt.
Yeah, this maybe I should subscript it with k, opt k. Yeah.
Okay.
This is my definition of opt k. Yeah. Okay, so to prove this, I'm going to prove a slightly simpler version. We're going to prove this from one side. Okay. We're going to prove that there is a subset S inside U such that U bar is the min S U bar cut. And the size of S is at most k minus 1. Note that if it turns out that the size of U bar was in fact at most k minus 1, then theorem 2 implies theorem 1, because you can simply take T to be U bar itself. And theorem 2 is already non-trivial, right? So even if the size of U bar is small, how can you show that there is a small sized S inside U such that the min S U bar cut correctly recovers U bar? So the theorem 2 is going to be the meat. In fact, once you have theorem 2, you can apply it from the other side. You get the conclusion, so corollary, you get the conclusion that there is a subset T inside U bar such that U bar becomes the min U to T cut, and the size of T is at most k minus 1. It's just applying theorem 2 for the cut U bar U, you get the same conclusion. Here I've exploited symmetry. Theorem 2 implies corollary 3, and then once you have theorem 2 and corollary 3, you get the right S and T. So use the S from theorem 2 and the T from corollary 3. This proves theorem 1. Okay, so fix S as in theorem 2 and T as in corollary 3. Then from here, you know that the sizes of these two are at most k minus 1. From here, you can conclude that U bar is the min ST cut. This is not very hard. So let's do a quick proof. Take an arbitrary, so let XX bar be min ST cut, and for contradiction, say XX bar is, let's say X is not U. This means that X intersect U is not U, or X union U is not U. One of them should not happen. And now you just do the standard uncrossing. So this is U bar, S is here, T is here by definition, and XX bar is something like this. Now look at twice the function value of U. This should be at least f of X plus f of U. This is because X is a min ST cut, U bar is a ST cut. And now apply submodularity. This is at least f of X intersect U plus f of X union U. Now X intersect U is this set. This is in fact S to U bar cut. And by theorem 2, you know that U bar is the min S U bar cut. So this should be at least f of U. And this should be, this X union U is U to T cut. And U bar is a min U to T cut. So this should be at least f of U as well. And by distinctness assumptions, I'll use this distinctness assumption, X intersect U is not U or X union U is not U. So this should be at least twice function value of U, and that's your contradiction. So X should be equal to U. So the non-trivial aspect is proving this theorem 2. Once you prove it from one side, you get it from, you apply it from the other side, and then the rest of it is standard uncrossing. Questions so far? Okay, let's prove theorem 2. I'm going to work under the same assumptions. Theorem 2. So let's look at the cut U bar. Action is going to happen inside U. Now, I want to find a set S such that min S U bar cut is exactly recovering U. Now, if I have a subset of this kind, let's call this something like Q. If I have a subset of this kind Q, whose function value is less than the function value of U, then min S U bar cut will actually find Q bar Q. And I have to, this is not good. So my choice of S would be incorrect. So in a sense, my choice of S should intersect any such Q whose function value is less than the function value of U. So let's call this collection C. This is the collection of subsets for which contain U bar, and the function value is smaller than the function value of U. These are the sets that my subset S that I want to find should necessarily intersect. So let's pick a minimal such subset. So let S be a minimal subset in U such that it intersects every such Q in the collection. Now, by this choice, you can immediately show that, so we'll show that this choice of S is going to satisfy these two properties. So the first property, let's prove this. This is the easy one. So it turns out U bar is the min S U bar cut. This is easy to show. So again, let XX bar be a min S U bar cut. And again, say X is not U. Then what does this mean? So recall that U bar should be contained in X bar, and f of X bar, the function value of X bar, should be less than f of U bar, f of U itself. This is because U bar is also an S U bar cut, whereas X bar is a min S U bar cut, so the function value of X bar should be smaller than the function value of U. And X is not U. But this means that X bar should be in the collection, which in turn implies that X bar intersect S should be non-empty, but by definition, the entire S should be in X. So this contradicts S contained in X. And that's your proof. The first conclusion of theorem 2 is easy. We did not use anything about submodularity or anything here. Okay? The rest of the proof, I'm going to push the usage of submodularity and symmetry all the way to the end. I'm going to avoid using it as much as possible, and then we will see where this is needed. This theorem 2, so far, to get the first conclusion, we did not use anything about submodularity. This is just picking the sets carefully. So the meat of the result is in proving that the size of this set is small. The size of the minimal set that we chose is at most k-1. Okay, let's prove this. So let's say this is not k-1. Let's say this is large. So let's say this S is U1 through UP for some P which is at least k. Now so we're going to prove by contradiction. Now to prove this by contradiction, what can we contradict? Well, we can only contradict the optimality, right? So this is what we can contradict, right? The function value of U is at most op k, we know this. So if we can find a cheaper k partition whose value, min-max value, is less than op k, then that would be a contradiction. So our goal is to find a cheaper k partition whose value is less than op k. That's where we're going to head. Okay, so let's see how to find this cheaper k partition. Let me draw this. So we have this U bar, we have U, I have U1 through u2 to some up. Now let's look at the min s minus ui to u bar cut. So let bi bar be the min s minus ui to u bar cut. So it certainly separates, so think of IS1. So we're going to do this for all of these p vertices, p elements, but let's look at u1. What is b1 bar? Where is u1 with respect to b1 bar? All of s minus u1 are going to be in b1, and all of u bar is in b1 bar. But what happens to u1? And the claim is that this u1 is in fact in b1 bar, and this holds for all p elements here. And this is not very hard to show. And let me first show this, and then we will see why is this useful. The reason is because of this minimal choice here. Let me call this 2. By the minimal choice of this S, there exists a subset Q in the collection such that S intersect Q is exactly UI and nobody else. Such a set Q should exist in the collection, otherwise S is not minimal. So such a set Q should exist. Now look at what is the function value on bi bar. Well, this is the function value on bi. Now Q is also S minus ui to u bar cut. So this should be at most f of Q. This is because Q bar Q is S minus ui to u bar cut. Q is in the collection, so Q contains u bar, and Q S intersect Q is ui, which means Q misses all of u1 through up except ui, so it's Q bar contains S minus ui. And since Q is in the collection, f of Q is at most f of u. So this means, so look at u bar. By definition, u bar is contained in bi bar, and f of bi bar is less than f of u, which means bi bar is in the collection. Bi bar is in the collection here, which means S intersect bi bar should be non-empty by definition of S, but all of everything except ui is already not in bi bar, so which means ui should be the only element of S which is in bi bar. Yeah, again, I did not use anything about submodularity here. This is again purely based on the fact that these are min bi bar is a min S minus ui to u bar cut, and S is a minimal transversal to the collection C. Okay, now let's draw the figure. What does this mean? So let me draw the bi bars. So if by this claim, what does this mean? b1 bar is going to look like this. It contains u1 and it misses all of u2 through up. And if I'm going to draw b2 bar, I get all of these. So this should be b2 bar. And if I draw b3 bar or bp bar, it's going to look like this. So you can think of these as fingers. You have the palm here, and each one of these red, blue, and green, each of these you can think of these as fingers. And the function value of each of these fingers is less than the function value of u. And recall that the function value of u is at most opt k. Okay. So you have a lot of fingers, all of which have cheap function value. They're less than opt k. Now the idea to get a cheaper k partition than opt k is to chop off some of these fingers, not in the literal sense, but this is how we're going to get a cheaper k partition. You have a lot of these fingers, all of whose function values are cheap. From here, we want to get a k partition, so we're going to take some of these fingers and create parts of the k partition. So that's where we're heading. Questions so far?
And this is where you'd want to use like this quasi-modularity to get the k partition.
Right. So from here, how are we going to get the k partition? Let's do the rest of it. So instead of looking at the action is going to happen in these bi bar sets. These are the ones which give us fingers. So let's relabel them and call these AI. So I'm going to call these AIs to be essentially bi bars. And without loss of generality, let's order these AI sets so that f of a1 is at most f of a2, at most up to f of a k. You note that we have k, at least k of these fingers, which will allow us to create a k partition. So we have p is more than k, but we will only use the k of these. Okay. Now, two claims. Claim 2. First, we are going to uncross the union of the first k minus 1 parts. So there exists a k minus 1 partition p1 through pk minus 1 of the union of these AIs, I equals 1 to k minus 1, such that f of pi is at most f of AI. For all of these i's. Let me state the two claims and then we will finish the proof and then come back and prove these two claims. The second claim, you note that we have only used up to k minus 1 pieces. So there is certainly something non-empty lurking here, right? Because of the kth piece, which is not present in the union of the a1 through ak minus 1. So let's argue about the kth piece, the function value of the remainder of which is the complement of these unions. So union of I equals 1 to k minus 1. Let's look at the complement of this. This function value is at most f of ak. Once you have these two, this immediately gives us that there exists a k partition p1 through pk minus 1 and pk, which is the complement of the union of these AIs, minus 1, such that the max of the function values of these parts, f of pi, is at most f of ak. But what is f of ak? This is exactly f of bk by symmetry. And f of bk, recall that bk should be in the collection. So f of bk is at most f of u, and the function value of u is at most opt k. And this is a contradiction. We have obtained a k partition whose function value is strictly cheaper than the function value of the optimum, and this should be impossible. Right, so this is how we're going to complete the proof. It remains to prove claims 2 and 3. I'll prove claim 3 first, because this again does not rely on symmetry. It will only use submodularity. Proof of claim 3. We want to show, let's write what we want to show. We want to show that the function value of the remaining piece is not too large. So let's look at the remaining piece. This amounts to showing that the function value of the intersection of the BIs, it's the just do the complement of the union is the intersection of the complements. We want to show that this is at most f of bk. And you can show this by submodularity. You can in fact show something stronger. The intersection of the BIs, I equals 1 to R, is at most f of bk. For all R, 1 to k minus 1 by induction on R. So the base case is easy. R equals 1. By this ordering, f of b1 is at most f of bk. So the base case is easy. Induction step, look at f of bk. Let's say we've proven this for up to R, and we want to show this for R plus 1. Look at f of bk plus f of br plus 1. By induction hypothesis, f of bk is at least the f of the intersection up to R plus f of br plus 1. This is by induction hypothesis. Now use submodularity. This is f of intersection of bi, I equals 1 to R plus 1 plus f of the intersection of the bi equals 1 to R union br plus 1. This is by submodularity. Again, I still haven't used symmetry here. Look at this set. This is in fact S minus u R plus 1 to u bar cut. Because the entire S minus u R plus 1 is present in br plus 1. So it is present in this set. And u bar is not present in any of these sets. So this is in fact S minus u R plus 1 to u bar cut, which means its function value is at least the function value of the min S minus u R plus 1 to u bar cut. So you get this is at least the function value of the intersection, I equals 1 to R plus 1, plus the function value of b R plus 1. Cancel these two, you get the needed. So this proof of claim 3 uses submodularity, and the fact that these BIs are min S minus ui to u bar cuts. And I still haven't used symmetry. I might have used symmetry in a weak form here and there, but not in the polymodularity inequality. This is going to come in the proof of claim 3. We want to show that the remaining piece, sorry, proof of claim 2. Claim 2, we have this union of these AIs, right? So let me draw the figure again. Claim 2 is saying, look at u bar, u, you have u1, u2, up to uk. We have these fingers. We want to uncross these fingers. So remember that we want a partition here. Whereas these A1, A2, they're going to cross. All these A1 through AK minus 1s, they're going to cross. They necessarily cross in U bar, right? They have intersection in U bar. So we want to uncross them and make sure that we get a partition. But when we uncross, we also don't want them to become empty. And here is where we are going to use the polymodularity inequality. Look at any two AI and AJ. Now, ui is going to lie in AI minus aj. And similarly, uj lies in aj minus ai. So they lie in this set. Now, we know by polymodularity that f of ai plus f of aj is at least f of ai minus aj plus f of aj minus ai. This is polymodularity. In particular, this means that if you look at, so one of the two inequalities should hold, f of ai should be at least f of ai minus aj, or f of aj should be at least f of aj minus ai. one of these two inequalities should hold. Now, if one of these two inequalities, so look at either one, if let's say the left side inequality holds, then you're going to uncross it by doing this. So you replace AI with AI minus AJ, and you leave AJ as it is. You still get UI is the unique, it's present in AI minus AJ, but not in the rest. And you have not increased the value. F of the set that you get is at least as cheap as AI itself. And if you're going in the other direction, then you leave AI as it is, and you uncross AJ with AJ minus AI. You replace AJ with AJ minus AI. And that ensures that the parts that you get, they don't have any more function value than the AIs themselves. You would have uncrossed them. And the reason that they are going to be non-empty is because of these UIs. UI is present only in AI, but not in any of the other sets. So when you uncross, you will never make these, you're going to subtract something, but you will never make this set empty because UI is present only in AI, but not in any of the other sets. So essentially, you repeatedly uncross via this postmodularity inequality, and that completes the proof. And that proves claim 2. Questions? Yeah, pretty much the entire machinery, the reason I like to present this proof is because the use of symmetry is pushed all the way to the end. Pretty much the use of symmetry and some modularity happens only in these two claims 2 and 3. Everything else is about picking some subsets and picking min cuts carefully.
So if I wanted, instead of a k minus 1, like a k bound, would certain things be simpler, or like, would the uncrossing be slightly simpler, or?
I don't know. This is not any difficult in terms of uncrossing, if you think about it.
I guess like treating the AK as something like a special. But yeah, I was just wondering, like, if a iterative, but yeah, like there's just a saving of 1.
Yeah, I don't know of simpler proofs. Yeah, this was something that, yeah, somehow, yeah, for hypergraphs, somehow we had to show a weaker bound. K minus 1 was not enough for hypergraph K cut. That was not working out because the objective was different and so on.
Right.
So there we show a 2K minus 1 bound, and constant bound itself was, yeah, I don't have simpler proof even for some constant times K bound.
Okay.
This is the easier of the uncrossing proofs.
And so again, yeah, this is just everything combinatorial is like non-combinatorial is pushed in the submodular minimization. So like this, once you have this, yeah.
Yeah, so everything is combinatorial. We have reduced it to min-ST cuts, collection of min-ST.
Got it. Yeah. And you'll talk about the assumption that the cuts are unique, or is that like a add-on that the initial assumption?
Yeah, that assumption is not very hard. You can throw you can add a graph with small perturbed edges over the ground set. Take a complete graph and perturb the edges by a small amount. This will make the function values unique, and it will not kill the optimum. There are simple ways to fix that assumption, and if you don't want to do perturbation and stuff, in the paper we do lexicographic tie-breaking rule to fix all of this.
Okay.
Yeah, that becomes a little messy, but when I was thinking about this problem, I was thinking about it under this assumption, and that's typically helpful. Uniqueness is helpful in these problems.
Yeah, but you used it only in the sense that to maintain the cardinality of this family script F. Like here, none of it kind of shows up.
No, that assumption shows up, right? Yeah.
Okay.
So the way I used it
Yeah.
to stitch the two, so I proved it from one side, and I used the corollary, and I stitched the two sides. There I used this assumption. So here, this is yeah. Why is this strict? This is because of the assumption, right?
Right.
Right. So yeah, these kind of things have to be overcome if you're not working with the assumption. But yeah, this is how I worked it out. So I like to present this proof.
No, makes sense. Okay. And yeah, like interestingly, as you said, none of it requires like non-negativity anywhere. Like all of this is
Yeah, non-negativity and monotonicity, these come in submodular maximization problems.
Right.
Yeah, so if you think about if you think about the problem itself, so look at this objective itself. If it is negative, then you can move, right? You can translate it, and you still get the same conclusion. Nothing is going to change. And same thing, the theorems also hold. If you translate the function values, then theorems still hold. So negatives should not affect the theorems. In a sense, yeah, that's how that's how I was thinking about it.
Okay, great. Thanks.
Any other questions on the proof? I think I've run over time. Let me switch back to the slides, and let me wrap up the talk. Right, so that's the proof, and right. So this is all I wanted to tell about the deterministic algorithm for min-max symmetric submodular k-partition. The ideas for this came from hypergraph k-cut, the deterministic algorithm for hypergraph k-cut. There we prove a similar structural theorem, but that theorem turns out to be much more difficult to prove because the objective is not min-max. It's a different kind of objective, so that turned out to be quite non-trivial. Yeah, so even we were conjecturing and checking that theorem was already non-trivial, and it was something that just that inspired us to do this. I won't go into that one. We have some more results after these works. In a sense, we also now have ways to enumerate optimum solutions. Recall that by Karthekeyan, you can enumerate all optimum solutions for both min-sum graph k-partition and min-max graph k-partition. Random contraction allows you to do this. And in fact, in the previous talk, I also mentioned that our algorithm, randomized algorithm, allows us to enumerate all optimum solutions for hypergraph k-cut. It is polynomial, and it allows us to enumerate. But it was a randomized algorithm. In a subsequent work, we have a deterministic algorithm to enumerate all optimum solutions to hypergraph k-cut. And in another work, which is under submission, we have a polynomial-time algorithm to enumerate all optimum solutions for min-max hypergraph k-partition as well. So the enumeration problem is also poly-time and deterministic. But there are some gaps between the best possible enumeration time. We still don't have the tightest time for enumeration. But for me, the more interesting open questions are the red fonts here. Can we solve min-sum submodular k-partition for larger constants k? And the smallest constants for which we still don't know to solve these problems are as shown here. It turns out we can solve these. We know how to solve these for min-sum submodular 3 partition. We know how to solve this. And min-sum symmetric submodular 4 partition, we know how to solve this. but beyond that, we still don't know the answer. So this is still open. All right, yeah, I'll stop here. Thank you very much for your attention. And I'm happy to hang around and take questions.
Are there other studied examples of symmetric? Like I know submodular is like extremely popular, but like beyond these cut functions, do you have good examples of symmetric ones? Or you can probably symmetrize the any function, but I'm just wondering what are nice examples to think of.
Yeah, I don't have any. That's a good question. I've also been pondering about this. I don't have anything beyond. You can symmetrize any rank function, matroid rank function. You can get symmetric functions that way,
Right.
but yeah, graph and hypergraph cut functions are the
So the canonical.
motivating examples for symmetric submodular functions.
And for like maybe for matroid rank, like symmetric version, or let's say not the symmetric. So like this k for larger values of k, is this known? Like maybe the first row min sum, let's say.
Okay. So this is an unpublished result. We have it in our. Yeah, we know how to solve min sum matroid k partition.
Oh, is that matroid union algorithm or something?
No, it's not matroid union. It's some. So this kind of structural theorem holds for matroid rank function.
Huh.
So yeah, that's something we're writing some notes about this problem. So yeah, we have it there. We haven't published it yet. We are still working towards the min sum submodular k partition. So
Okay.
yeah, we looked at rank function and we are able to solve that.
For large like constant values of k.
For constant k, you can solve it in n to the k squared time. Again, same complexity.
Okay. Nice.
And I'll leave that board. The link will be on, so in case people want to look at it after the talk, the board will be there.
Okay, are there any other questions from anyone else? Okay, let's thank Karthik again. Thank you.
All right. Thanks, everyone.